and thank you for coming to this seminar. So I will speak today about thermoluminescence, but I will focus on something like more general, rather than no physics and no special chemistry, but all material in the Louvre Museum. It's the most famous museum in Paris, with a very huge museum and thousands of masterpieces in this museum, and they use thermoluminescence. I will show you that in a moment. So first, I would like to introduce you. So this is the main Louvre entrance. There is it's about a square like this with this kind of building, and in the main place of the Louvre, there is I think for more than 20 years now, a pyramid, which is the entrance for the visitor of the Louvre. And there is also a research lab very close by. Below this part of the Louvre, there is a research lab, and I will tell you a little bit more about what can be done with thermoluminescence in this lab. And my institute in this part very close by. So this is the Louvre, and I am here, and this is also an old School of Chemistry. And so this part is this is an old picture of Paris. So the Louvre is there. No, the pyramid is there. And my institute is in so-called the Quartier Latin, where there is a huge number of very old and small institutes. You see, the institute is quite small, and I will tell you a little bit more about that. So, of course, there is a lot of masterpieces in the Louvre, famous, and there is also ceramic, plate, potteries, and so on. So, very different kind of materials, and with painter and different things. And I will show you what is the interest and some example of thermoluminescence for these activities. Concerning my institute, we are so small that we put that in a so-called Paris Tech. It's to have like a general name, and it's try to gather more than 10 institutes. Small institute, it's about 300 students, only 300 students by institute. So they try to gather, and you can see, for instance, Paris Tech is agronomy. There is a Statistics Institute, Telecom, School of Economics, for instance. HEC is a famous School of Economics. And so, for instance, we use HEC is the top, according to the Financial Times, this year Financial Times. HEC is #1 in the world for the master in international finance, for instance. And for the ranking, we need to be a little bit larger than a small institute. So we try to gather, and that's why oops, sorry, I have to go on this side. So we try to gather very good, for instance, École Polytechnique is also famous in France, and Les Mines or HEC, and so there is and we are the only institute which are in charge of the chemistry. So we are focused on chemistry, and of course, Institut d'Optique is focused on laser, but it's very, very easy to communicate through the Paris Tech Institute. We have a possibility of exchange of students and so on. So, French education system, it's quite complicated. It was done by Napoleon more than 200 years ago, and he decided to have the university. This is a classical university, like you have here, probably. And besides the university, there is the so-called high school. High school is not, after high school, it's engineering school. We call that Grande École. That means Grande École is high school, but in terms of high-level school. And what's the difference? There is selection here. So the university in France is free. There is no selection. Everyone can go to the university. But the level in the university is quite poor, at least at the beginning. And this is I will say the master part, the best students are going from high school to this class preparatory class. And so sometimes in some country, you have some selection just after the high school. Here the selection is 2 years after the high school. There is a very difficult 2-year preparation program to go to the engineer school, Master of Engineering. So engineer is not the same meaning as in the US. Engineer is not technical. Engineer means in France it's the top of the best person. Everyone doing even politics and so on are coming out from this school. For instance, HEC, there is a very competitive. It's a very competitive school, and there is also people are coming from this highly selective part. And you see, after the some people doesn't want to do some to go to the industry at this time or in the private company, and they decide to go to the doctoral study. And this is why people at the university are in competition with people coming from this place. And there is also people who are like a short, within 2 or 3 years, to have a, this is really a technical preparation. So this is a engineering school. It's only 3 years. And after they can move either here or go directly to university for the best student. So I think this is a very elitist way. And this is the only school where they are wearing special clothes and this kind of school. This is, for instance, Polytechnic. There is a few schools they are wearing some clothes like this. In France, it's at the university. It's very everyone can wear what they want, and so very easy to go to university. But after, it's difficult to go to doctoral study and to have a position after the university because there is a big competition with people coming from this part. So I am working in one of these institutes called Chimie Paris Tech. So it's a very small institute just in the center of the, so it's quite elitist to be in this institute because there is a very, you see this is only 100 graduate students every year. So you see this is a student from last year. There is a director of the institute somewhere. I don't know exactly, here maybe. Yeah, she is there. And this is a woman. And there is only 100 graduates, so very high level. So it costs a lot for the study are free in France, so the student doesn't pay anything. And to have 100 graduate students with almost 50 professors is very expensive in comparison to the university. The university is the opposite. So, and in the School of Chemistry, we are supposed to do all the chemistry. So there is different lab, and I am belonging to this lab, material for the photonic and optoelectronics. And there is another part, which is material for the memory of history. And this is, they are directly working with the Louvre. So there is direct connection from this guy, Didier Gourier. You can see several papers when I am working with Didier Gourier. He is in charge of this group, directly working with the Louvre, and he is in charge of the analysis of the masterpiece of the Louvre, and etc. Okay, so now I will move from my this presentation of the French way to at the university and the Grande École, and I will show you some example at the Louvre Museum. But first, thermoluminescence. Some of you are not familiar with thermoluminescence, so I will go a little bit first a little bit in detail about that. And the first observation of thermoluminescence comes from this guy, Robert Boyle, from Ireland. And he was a chemist, physicist, philosopher, and he did, at this time, the scientists were doing a lot of different things. So this guy discovered first the emission coming from a piece of diamond, which it was loaned by him. So there is different story. One story is that he put his piece of diamond with him in the bed, and he realized when he was close to his body, the elevation of temperature led to a small luminescence. Then he moved to and what is he published? He moved to a flame of the candle, and he observed a luminescence coming out from this piece of diamond. So this is a book. You see, this is a book when he put. So this you can see the name here, Robert Boyle, and he described 12 observations presented in 1663 on luminescence from a piece of diamond which are loaned to him to do this. So simultaneously, a little bit after, this guy also was working at the Royal Society in London, and he also tried to make some complement information about the thermoluminescence and this effect. So the thermoluminescence is the process of thermally stimulating the emission of light from a substance following the absorption of external energy by that substance. So in general, there is external energy source used to induce phosphorescence, it's called phosphorescence, or immediate afterglow. And there is, after the preliminary study, the development start after the discovery of the radioactivity in the late 19th, early 20th century. So I will speak about delay fluorescence a little bit later. Two important persons for this. For the earliest observation of the optical stimulated luminescence, Becquerel, Edmond and Henri Becquerel. And they look at the infrared stimulated zinc sulfide and cadmium sulfide. And look at this spectrum also. Even, I think at the mid of the last century, you see they did some OSL, it's a phosphorescence with infrared stimulation of this material. So it looks quite new and quite important to do, but it's already known long time ago, I guess. By illumination with infrared light, we can observe some luminescence coming from this strontium sulfate. Important word, the word luminescence and thermoluminescence was first defined by this person, Wiedemann and Smith, more than 1 century ago. They tried to explain the dissociation, separation of charge, and recombination to produce luminescence. At this time, they tried to a little bit understand what's happened. What can have recombination after a long time? And they were already talking about separation of positive and negative charge. That means a storage of charge. And then came the word phosphorescence from Becquerel, radio photostimulation, photostimulated phosphorescence, etc. And finally, optical stimulated luminescence by Fowler in 1963. So this is a few historical of the thermoluminescence and optically stimulated luminescence. So if you look at the publication of thermoluminescence or thermoluminescence, you can clearly see that the first paper came out 1914, but 0 citation. The guy was unlucky. And then a lot of things appear. I put this schedule because the effect of irradiation of solid was very important, and thermoluminescence was used for irradiation dosimetry and archaeological datation. So very important period with a lot of publication on this field. And suddenly it's decreased because of the age, probably of the age of the scientist also, and because there is a renew in the 90s with the discovery of persistent luminescent material and new thing I will tell you a little bit more after. So let's illustrate the thermoluminescence with the well-known energy level diagram coming from the valence band and conduction band. So this is a classical recombination from valence band, excitation and emission from the valence band. And when there is some traps, either electron traps or hole traps, instead of having the recombination, you can have the storage of the electron or the hole in this trap. In that case, there is no more recombination because one part of the electron or hole is trapped. And you can induce the recombination by a release of the traps. In general, it's through the conduction band. And if you have heating, so this is the thermoluminescence. This means you are heating. You can release the electron, for instance, for the trap. It's the same concerning the hole traps. And according to the trap depth, there is one thermoluminescence peak for this depth. And when the trap is a little bit deeper, for instance, in the case of the green traps, E2, there is a peak at the higher temperature. So you have a direct link between the temperature and the trap depth. And you have the same thing can occur with all traps. So this is the basic of thermoluminescence, historical and a short presentation of the energy level, what they are presented here. And if you look at the fundamental of persistent luminescence, for instance, you have this kind of schematic. And you see there is three kinds of traps. Deep traps, which are interesting for datation of dosimetry. There is what's so-called shallow traps and average traps in depth. And this one are used for persistent luminescence. And this is mainly related to the afterglow, shallow traps. And this is a recombination, a classical recombination. So, of course, to measure this kind of phenomenon, you need a scientific apparatus. So what kind of apparatus? You need one sample. First, an excitation coming from X-ray or UV irradiation, for instance. Then you need to heat the sample. You heat the sample either by regular heating in a furnace, or you can have a release of traps by the lead or laser. So this can be in a CW, continuous wave, or a pulse or ramp mode. Then you have thermoluminescence or optically stimulated luminescence coming out. Then you have to use a detector, PMT for instance, to measure the emission in the visible, and to use a filter in order to cut, for instance, one part of the light. So this is the classical way. So what does that look like? This looks like this, for instance, in the Louvre Museum. This is a OSL thermoluminescence reader. So it is a Rizzo DA20 automatic with excitation coming from gamma ray, for instance, or beta irradiation. Photomultiplier, so this is a detector. And you have the sample order and so on. So you put your sample inside and you can measure directly the light coming out after heating. In the lab, we have something to go at lower temperature. So this is a setup in the lab. We are excitation either with X-ray here, or we use directly UV radiation from this side. And this is the way to have low temperature and high temperature. Here in Kyoto University, the cryostat is not horizontal, but it's vertical, but it's the same, exactly the same principle. Of course, you need optical fiber, for instance, or the detector coming out from optical fiber, camera, and so on to detect the photon coming out during the heating. So simple, quite simple experimental setup, but behind this, I will not put a lot of science in this presentation, but there is a high-level science coming out from the traps recombination. So this is, for instance, what you can observe from the trap depth of E in electron volt, and there is a frequency factor S, and you have the thermoluminescence intensity coming out from this equation. So you have one trap, one center model, and you can have several central models when it's several order model. So well-known Randall-Wilkins first order group peak look like this. It's an asymmetrical peak. Well, you can see the shape here. And this is the expression a little bit more complicated, which can be solved in order to have to extract the parameter. So the parameters seem quite simple when you look at this kind of traps. You have the activation energy and the frequency factor and the number of trap electrons, for instance, or trap hole. This is a symmetrical way. In fact, when you look in detail, for the more realistic model, you have to look a little bit more, and you need to add different trapping probability, retrapping probability, and so on. So the model is a little bit more complicated. And in general, you have to test different models to know which is the best model. So if you look at the Adribos paper from Netherlands, you can see the guideline for the extraction of trapping parameter from the thermoluminescence blocker. He explains that, of course, you need function of temperature, function of the dose, UV or X-ray dose, for instance. You have to control this. Function of the heating rate, very important, is to control and to move the heating rate in order to have the information about the mechanism. You can use a thermal cleaning. You stop at one point and you wait for a while until it's completely clean. And you have to apply different methods to double check. Inertial rise, etc., peak position. So this is the tool that is well known to extract the parameter from thermoluminescence. Okay, now I will move to some example. I would like to show you in detail now some example. First on datation and dosimetry, and second part on persistent luminescence and afterglow. So datation and dosimetry. Dosimetry, everyone is familiar with that. If you are doing some X-ray diffraction, for instance, you are supposed to have a dosimeter close to the apparatus. And this is controlled every month or something like that. And if you are working with a high energy level, you have to control your irradiation. Datation is, for instance, the use to have some age of unknown material. So I will focus a little bit more on this part because it's interesting and not well known, I guess, for most of you. And the key point for the datation is that you will use by a solid has been irradiated with a dose Q0 during a time t. You don't know the time t, it will be the age of the material. So you have the number of traps, and you should use a calibration. Very important is the calibration. Then you know approximately the concentration of traps corresponding to a received dose. And you have the radiation time in laboratory, the source, in comparison to what was you wanted to observe. This is the dose received by the objects that you want to determine the age. And this is the time. And you just have to divide. So this is called paleodose. This is the dose received by the object during all the years that he stays within a space. So, for instance, if you put something in this room, an object in this room, you cook something. For instance, you cook a pottery in the room. And if you keep the pottery in the room for several hundred or thousand of years, the pottery will accumulate the ambient radiation, and you can follow in case of deep traps, you can release the trap by heating the pottery and to know its age. So if you know the annual dose, the age is the dose that was trapped in the material divided by the annual dose. This is the calibration over there. So this is another way to present. You have the intensity. For instance, natural mineral, irradiation over millions of years. The traps should be empty for the T0. Very important is the T0. That's why, in general, we are using that for pottery. Because the pottery, you put the pottery in the furnace. That was done for, in the past, 2,000 years ago, they were doing the same kind of pottery. They did a fire, and they put the pottery in the furnace. It was a T0. At that time, all the traps coming from the raw material were released. So when they are cooking the pottery for the first time, it's a T0, it's the beginning. And then, during, for instance, during several thousand years, there is a natural radiation, and there is an increasing number of traps. And then you can measure the traps by thermoluminescence. Thermoluminescence, you release all the traps. You put your material in the furnace, or the thermoluminescence setup, and you control the quantity of photon coming out, and it can be double checked by up here, the quantity. And you have information about the time and the datation. So this is the way to do this. So some example, of course, very important is to know the natural irradiation of the, this is not so easy, and you have to control this. For instance, if you can find a pottery around here, you need to control also what is the natural dose. So this is this red peak show you the natural irradiation. This is the peak coming from energy, spatial energy, and you have an information about natural irradiation around the surrounding of the place where they discover the pottery or something like that. So you measure. So another example of natural irradiation. This is, for instance, you can simulate the, for instance, 72 hours of environmental radiation here, and 15 hours. And this is a calibration dose, for instance, corresponding to this 43 microgray of irradiation. So you can do some kind of irradiation like that, artificial irradiation, to approximately know what was the environmental irradiation. In the lab, you can try to simulate the radiation coming out from the field, from the exact field. So first example that I want to show you, in the Louvre there is a lot of pottery like that. They are coming from this part. I think I have another one. Okay, this part of Greece, Tanagra. So it's approximately 53 kilometers from Athens. So you see, it's not the Shinkansen. 53 kilometers, 1 hour 14 minutes, because the road in Greece are very narrow, and you cannot go very quickly. So if you look at this pottery, very famous pottery, they were painted and they were made 330, between 300 and 330 years before Christ. That means around 2100 years from now. Okay. So, and there is a lot of things like that. You see, there is several books speaking about this Tanagra painting on the right side. So this is some example, and there is a name. Of course, this is in French. So there is a name, danseuse voilée, for instance, with the edge, and there is several Tanagra, around 200. There is around 200 pottery like that in the Louvre. So what's happened? Okay, Tanagra place first, very famous, cited by Homer, the place of confrontation between Athens and the Peloponnese at 457 before Christ. This is where the Philipstein gathered before the Battle of Delian at this place. So it was a famous place here, and there was a historical important place in old Athens. So for instance, this is a beautiful Tanagra statue. So the name is Woman in a Blue Coat with Fan and Sun, you see, very, very beautiful. There is another one here. And this is, for instance, a figurine of a woman trying. This is a figurine of a woman also. So this is some example of this thing. Tanagra means teenager of remarkable young woman with grace and finesse. So the first collection arrived in the Louvre in 1872, and a lot of pottery arrived at this time. Immediately after, some false pottery appears. This one is a false pottery. It's not made 2,000 years ago. And the age of this pottery it is coming just after. You know, in the Louvre, it was very popular at this time in the Louvre. Immediately after, several hundred of new Tanagra appear in the market, and it was a false. So now in the Louvre, with the thermoluminescence, they try to look at the authenticity of the different Tanagra. So they use thermoluminescence. For instance, this is a thermoluminescence profile. You see it's coming from room temperature. So they no need to go at below room temperature. With a Rizzo apparatus, it's classical to go from room temperature to 600. So this is the profile of the thermoluminescence of the Tanagra. The red signal, this is a natural thermoluminescence, red signal, and the thermoluminescence coming from the original Tanagra. This is a false Tanagra. So this is the signal for contrafeit, this one. And you see that the Tanagra and the natural irradiation are very different. So it's impossible to have something made with raw material which are not coming from the old age, of course. That means it's a false one. So this one are from the late 19th century. And therefore have been little bit submitted to the ambient radioactivity. So this is a Tanagra responded by thermoluminescence, and this is a natural thermoluminescence here, in this case. So you can see this is the frequency of the fabrication of the Tanagra about 2,500 years ago. The Tanagra was fabricated in this scale range, and a second population of Tanagra appear very close by, I think, between 200 and 300 years ago, and between 200 and 300 years ago, this was a false Tanagra, of course. So this is a statistic of all Tanagra investigated by thermoluminescence. You see, there is some are coming from this age, and there is some original, but original are still coming from almost 1,000 years. So it was famous to do some Tanagra 1,500 years ago till 3,000 years ago. I mean, during more than 10th century, they were doing Tanagra like year after year and different Tanagra. So this is 150 pieces analyzed and by thermoluminescence, for instance. So I put some advertisement of what. Of course, there is this is an uncertainty of the age because of the moisture and the evolution of the Tanagra within the age. So it's difficult to have a precise age. So there is uncertainty, which is quite big in large. You see, something like 500 years uncertainty. So, but you see, definitely we can say this one are authentic and this one are full Tanagra. So what is the methodology to do that? Of course, they have to manipulate with care without energetic light. So when they collect the statue, they have to keep it in the dark. Otherwise, we will have optical stimulation and the level will decrease. So this is, for instance, an example of bronze manipulated under red light to avoid erasing the signal when handled. So this is not so easy to manipulate. Another example, Chinese burial caravan belonging to the Tang dynasty. And again, it was important to know if it's a real one or false one. So this is an example of these two. So are they belonging to the Tang dynasty? So this is 600, between 600 and 900 after, in France we call that Christ, after Christ. I don't know how you call that here in Japan, but in France we say 0 is before Christ and after Christ. So this Tang dynasty is about 600 to 900 after Christ. So this one was purchased in 1939, and it was important to test the age. So this is an example, for instance, of this type of pottery. So this one are the good age. But this one, for instance, is coming from was done in 1925, plus or moins 10 years after Jesus Christ, okay? So very close to the other one, but this one is not a good one. Another example, jade in China, very important in China, rock in China, and the true jade is coming from this solid solution between two natural minerals. And by trap density and thermoluminescence, you can work and can characterize the origin and if it's a real one or if it's something like it's not coming from the good place. So for instance, I would like to focus another example. In this part of close to the border of Portugal in Spain, so this is Spain on this part and the Portugal, there is on the wall a very old carving, rock carving on the wall. So they try to determine also the age of this. So when they discover this kind of carving, they were looking on the wall and they remove everything and they remove what was against the wall, and they try to look at the edge. So several techniques was used: carbon 14, mass spectroscopy, and so on. But it was very difficult to date and quite impossible. It was impossible to have a reliable edge for this thing. So they tried with thermoluminescence coming from the raw material that was just with that, because besides this type of graving, there was some fragment of quartzite, and they look at the fragment of the mineral which was close to this kind of carving. So this is the datation of 3 sites in this part of Portugal and Spain. And you can see one was 30,000 years old, one was around 10,000 years old. The calcite was heated at the time of the wall decoration. So it was possible to find, besides the carving, some pottery or some stone which give you some information about the date. So very interesting way to have information about that. But sometimes it's not working so well. This is an example of thermoluminescence datation coming from Iran, this site of Iran. And they look at the one part of pottery, you know, this is a small part of the pottery coming from this. And they try to find the edge. But you see the discrepancy is too large. You see it's between 1,000 years, 2,000 years. So this data are very dispersed. And it was impossible to have a good accuracy of this kind of this age. So, in the Louvre, it's not the only way to do thermoluminescence. I want to show you that besides the museum, there is a research lab. And this is another very strong apparatus that is beside. And the name is Accelerator Grand Louvre, Aglaé. So this is to have another technique of radiation by high energy irradiation. And for instance, it can be used, if you look at this, this statue, they wanted to check the origin of the AIDS. So the AIDS from this very old Babylon goddess, 143 years before Christ. And they look at the AIDS, and the AIDS, the formula of the AIDS is chromium it's a ruby. And they look at the impurities coming with the ruby. So this is a particle-induced X-ray analysis, so coming from this. And they look at the signature of the impurity, and they can determine that the ruby are coming from Burma, so we call that Birmanie in France. So this is a part in Asia, and they determine the origin of the ruby from this statue in the Louvre, for instance. So
here, X means impurities
yeah,
other than chromium.
Exactly.
Right?
And they look at the impurities, and from the quantity of impurities, you can determine in which mean of which part of the world this is coming, the ruby. Of course, in the lab, the ruby, if it was artificial ruby, nobody put vanadium, titanium, iron, gallium, and so on. And I mean, it's no use to do that. So I hope that I convince you that thermoluminescence is a good tool for datation and application in datation and dosimetry. I will move very fast now in this part. Fast because I did that for most of the students in the Professor Tanabe lab, and I will show you this now. So dosimetry, also, just an information about dosimetry. Maybe you are not familiar with dosimetry, but this is a kind of application that you can find for dosimetry. It's just to control the intensity of what you receive during the exposition to high energy, for instance, or neutron or so on. So they use this kind of dosimeter. So and this is very important for homeland security, for instance, in the airport and so on, or for environmental security. So now I will move a little bit faster to persistent luminescence and afterglow. So persistent luminescence and afterglow, this is this part of the traps. So that means shallow traps and the trap between deep traps and shallow traps is called useful trap, for instance, for persistent luminescence. So a traps here with a signature in thermoluminescence around 300 Kelvin, that means room temperature, and you have persistent luminescence. So this is what we study in the research lab in Paris, and it's very important to have, for instance, material for medical imaging for different applications. This is, for instance, this kind of apparatus to control the tumor, for instance, or to control the metabolism. So this can see accumulation of tumor, for instance, by a PET scan, or this is to control the metabolism. This is the circulation and the good functionality, for instance, of your brain. This is a brain with a normal brain, with excitation of the brain. You are asking questions to this guy. This guy is normal. Just to try to ask difficult question. This is a guy doing some PhD examination, for instance. And this is a person with Alzheimer's, and you see the irradiation, not irradiation, the circulation is prevented, is very bad. And even when there is stimulation, there is still some problem in Alzheimer's part. So in the lab, we are working on this kind of material in pixels, which are inside the apparatus. And it's very important to control the quality. And in this case of position emission tomography, the key point is the persistent luminescence. We have to avoid the persistent luminescence. This is, for instance, very old image, the tomography with very old image. You see there is a very low, the images are not of very good quality, while this is a more recent image, and you see the quality are very good. You can clearly see some details. And between these two, there is an improvement of the apparatus. It's very clear. You have good apparatus, you can do some very good image, and when the apparatus has some persistent of afterglow, the image are blurred and very bad quality. So in the lab, we demonstrate that in this kind of material, LYSO doped with cerium, the origin of the trap was a type of oxygen vacancy, and we succeed to put dopant to limit and to decrease the afterglow. In that case, in the next generation sold by Philips, the apparatus have much less afterglow than the previous one. This was done also for X-ray tomography. It was exactly the same approach. And for the tomography, you have also to move very quickly either the X-ray source and the X-ray detector to do some tomography and to do some tomography within a few minutes, for instance. And the same, we use thermoluminescence. Here you can see the thermoluminescence curve. So you recognize the thermoluminescence glow curve around 300 Kelvin. This is the room temperature. And you see that when you decrease this thermoluminescence peak, there is no more afterglow. Here there is very low afterglow here. I will show you in 1 minute. And here there is a very strong afterglow. So this is the decrease of the afterglow when you are moving from one kind of material to another kind of material. So that was a recent patent that we got with Saint-Gobain for this kind of apparatus. So in some case, we need to enhance the afterglow. So I put this because we would like to have persistent luminescence on the good side. In the good side is here because, and in the bad side. So this is you can recognize here the female. That's I think this is the bad side because there is a cold and ice. Okay, I don't know why they put the female here, but you should tell me. And so we would like to put persistent luminescence on both sides and to enhance persistent luminescence. So I came here also at Kyoto University, and you can see, for instance, this is amazing. This is a picture that I took for a small exhibit of Professor Tanabe, and there is no excitation here. The excitation was cut. This is a reflection of the lamp. You see that the lamp is there, and you can clearly see that there is still very high luminescence, clearly seen by the haze after several minutes. And this is a group. You can recognize most of the person here. And you can see that it's important to use this material to enhance persistent luminescence and to do some material with a lot of interest. So we can call that also optical battery, because in that case you can store in the battery the energy, and you can release the energy after several hours. So it's very interesting, for instance, for this kind of application, for the exit sign, or for lightning, or for different application, LED now, or something like that. So very important field, and I am pleased to see that here in this lab there is a lot of activities, very nice activity of this. So in Paris we try to use this activity, we try to look at this activity to do some optical imaging, to use at bioimaging with persistent luminescence. So if you look at the persistent luminescent and long-lasting phosphor, there is a lot of papers starting after the main publication about strontium aluminate, co-doped with europium and dysprosium. discovered here in Japan. And you see, but in vivo imagine, you see that 2014, there is already more publications than last year. And that means that at the end of the year, we will have maybe 2 times more publications than in 2013. So the field is really increasing very quickly. And I am pleased to see that several other labs are looking at this for application. So what's interesting is that we can do, I will only need 5 more minutes, and sorry for to be long, but we use the transparency of the body in the near-infrared range. So, and the way to do that is to use persistent luminescence. So you use the persistent luminescence to look a long time after the injection to the animal at the emission. So we call that time management, and we propose to use that for to do some image of tumor and different applications. So of course, again, thermoluminescence is very important. I told you in my in the title that this is from thermoluminescence. So thermoluminescence is very important to analyze the traps and to try to look at the mechanism. So this is a mechanism where you are pumping at 2 different wavelengths, for instance. So thermoluminescence, very efficient tool to do that. After, of course, you need to prepare the material. And in that case, this is nanomaterial. You need to prepare small size material in order to have a circulation within the body. So this is an example of this kind of material with PEG, for instance, with hydroxyl and with other functionalization with positive, negative, and neutral coating. And you see, this is what happened. This is the animals, and you have injection of the nanoparticle. Within a few minutes, in the case of positive and negative charge, the nanoparticles are directly trapped either in the lung or in the stomach here. If you put neutral nanoparticles, you can have circulation of the nanoparticles within several minutes, and it will stop at around 30 minutes, I guess. And you see, you increase the circulation. So this is what was done for the first publication, in fact, 6 years ago. And you can clearly see that in the PEG, this increase of the circulation because of the neutral charge of the nanoparticles. So what we did recently was to use this nanoparticle to localize tumors. So this will, you can see here, tumors localized with the use of the nanoparticle inside the small animal like this. So it was published recently this year by Thomas Maldinet, for instance. We also look at the role circulation and ischemia. This is a good example of the use of nanoparticle. This is a liver, and you can see this is the shape of the liver, and we cut the circulation of the liver, of half of the liver. And we prevent the circulation of blood in this part of the liver. And then we block the circulation, and then we block the circulation to put some pressure, by some pressure. And then again, we look at the recirculation. That can happen, for instance, if you have an accident you are cycling and you have an accident, and suddenly you have a very bad circulation of your legs, and you can check if the circulation is correctly what's happened with the circulation, and there is a recirculation. We call that ischemia and vascularization. So ischemia is when you cut the circulation, and vascularization again of some organ. And we saw that after 5 minutes, there is again, by this kind of nanoparticle, we can see that there is again the circulation. And this is, of course, due to we put injection of nanoparticle inside, and we follow the long-lasting persistent luminescence of this. We follow also administration of medicine, and you can see, for instance, 4 hours after the administration, what's happened to the medicine. This is, for instance, nanoparticle in water, and you see it is going here, and after 4 hours you can see the dispersion of the medicine, and you can see that after 1 day there is still the active medicine inside the body of the animal, And it was impossible to determine by other techniques. This is the classical way to determine if there is still some medicine, active medicine inside the body of the animal. So in that case, that means it's not necessary, for instance, to take a second pellet. Sometimes you have to take a pellet every 6 hours, every day, and so on. So in that case, you can look at the dispersion and the way that the medicine is dispersed inside the body and follow the nanoparticle inside the animal. So that was 2 examples. Of course, I would like to finish by showing you that there is a lot of new work on these kind of things. That, for instance, in vivo and living cell using persistent luminescence, drug delivery and tumor targeting, multimodal persistent luminescence and NMR nanoparticle. There is also upconversion and persistent luminescence. So very different things made by this kind of persistent luminescence nanoprobe and bioimaging. There is, of course, only image of animals, because to go from animal to human is a different story. You need to have several years. So there is animal like a pork, small animal, a rabbit, and so on. So in conclusion, thermoluminescence, it's an old technique. We can be used for new material and future material. You have seen some example, for instance, of the use for detection of pottery, sculpture. It can be used also for determination of dental. For instance, if you find a dental coming from a squale, for instance, you can use to have the edge also of the animal. And you can use that for a new application, like dosimetry, new LEDs, and medical imaging, for instance. So I think this field is full of interest. And I would like to thank you for your attention. And I will be pleased to answer to your question. So thank you again for your attention.